There's a problem though, right? There's a problem with what we just did. Let me just make this a little bigger. So our problem is that here we're integrating this from 0 to delta t. That's a delta t if you squint hard enough. So we're integrating an equation that's in terms of delta m over delta t. So what happens if there's a mismatch between those two boundary layer thicknesses? At some point, you're going to, let's say you're integrating, let's say that the delta t is greater than delta m, right, which means Prandtl number less than 1. So if Prandtl number is less than 1, then I get to a certain point, integrating delta, you sort of get to the edge of the delta m boundary layer, the momentum boundary layer, and you're still assuming that there's a velocity profile that's changing based on this equation u infinity 2y over delta m, right? There's no criteria there that says I'm inside or outside of my actual velocity profile. So eventually, if you integrate far enough, you're going to start getting error in your solution. So this integral is actually only valid when Prandtl number is greater than 1. When the velocity profile is, the range of that is sort of sufficient to cover the full range of the temperature profile. Right, so we'll write it this way where we say, this is our solution if the Prandtl number is greater than 1. If the Prandtl number is less than 1, then we have to do something else. Well, what else could we do? I won't make you write it out, but what else we could do is we could break up our integral and we could say the first part of my integral from, I got to make this bigger, sorry. Let's just do it this way. So the first part of my integral is going to be from 0 to delta m. And remember, this is the thermal equation, so we're trying to get to delta t. So from 0 to delta m, this is valid. Once you hit that limit, now I have to do something else with my velocity profile. So I'm going to integrate that first, and then I'm going to add to that the second part here, which is from delta m to delta t. Now my velocity profile is what? It's just u infinity. It's just a constant. So now my energy equation is being applied with this velocity distribution, which is just a constant u infinity. And then that's equal to the same thing on the right-hand side. Okay. So that it's just something it's like an extra step you have to do. The last thing that you might need to do or might want to do is what happens if Prandtl number is much, much less than 1? Meaning what? Meaning my thermal boundary layer is a lot less than my momentum boundary layer, almost negligibly smaller. In that case, I can actually just assume the entire thing is at u infinity and do the full integral that way. Okay. Any questions on this? Okay. Very clear today. All right. Cool. So let's a couple more things to do here. Let's get to the point where we can actually compute H and Q dot, right? Because we have our velocity profile. We now have an ODE, but we want to get to the point where we can use it to evaluate heat transfer. All right, so let's see. We're going to take, let's move on under the assumption that this is true. This one here, this one's true. Prandtl number is less than 1. So we're going to take that and continue on here. So this is where we are going to start with our integral. To evaluate this, let's see. First, we have to decide what is it that we can bring out. So this problem, again, we're saying T infinity minus TS is a constant. Surface temperature is a constant. So that can come out. And we end up with ODE that looks like this, d dx of u infinity that come out, or that already was out. And then we have TS minus T infinity times the integral from 0 to delta T of 2y over delta m minus y squared over delta m squared. Okay, times what's happening over here. Now we have 1 minus 2 times y over delta t plus y squared over delta t squared. All that integral was with respect to dy. Okay, and then on the right-hand side, we have 1 over rho c times k times ts minus t infinity 2 over delta t. Okay, so that's just taking one step and simplifying this a little bit. Our main challenge here is this, I guess, this integral. So we just have to do this integral. I mean, it's not challenging. It's, you know, Calc 1. You can just expand out the terms and make the evaluation. If we do that evaluation, there's kind of an intermediate step that's important though. So if you do this evaluation, this particular integral ends up being delta t squared over 6 times delta m minus delta t cubed over 30 times delta m squared. Okay. One thing that you want to do here, in order to get this as, like, remember, we're trying to get this to an ODE in terms of delta t. So we have delta m appearing. We have to figure out kind of how to make that go away. Well, if you look at this, we can take out delta t from both of the terms, and we're left with delta t to a power over delta m to that same power. So if we do that, and we make the sort of remember that what Prandtl is equal to delta m over delta t squared. Remember that fact. And remember that the Prandtl number is a fluid property, right? That is a property that is not going to change depending on the location or anything like that. Then we can really simplify this down just in terms of delta t. So we do that, and this ends up being what? This integral ends up being delta t times 1 over 6 square root of the Prandtl, PR, minus 1 over 30 times the Prandtl number. So that's what this little integral ends up evaluating to. So that greatly simplifies everything, and we can now get to a point of writing this. So let's see, we do the integral. Yeah, I'm going to end up skipping forward to give you the result here so we get to everything. So we end up with solving the ODE. We get delta t is equal to the square root of 4 times alpha. Alpha came from k over rho c times x divided by u infinity times this kind of messy thing up here. Let's just, for the sake of ease, let's call this a. So this is no, I'll just write it. So a is equal to 1 over 6 square root of Prandtl minus 1 over 30. Sorry, this is 1 over 30 times the Prandtl number. Just call that a for now. Okay, so now we've now have this solution for thermal boundary layer thickness, which is great. This is partly what we were trying to do. Now we need to get heat transfer and flux. So let's go back to our rate equations where we say, okay, q dot double prime s. This is from our, you could look it up in the table again, but it was 2k over delta t times ts minus t infinity. We have now delta t, so this is saying, what this is saying, h is actually equal to 2k over delta t. And if you substitute in our delta t, then that's saying h is equal to 2k square root u infinity times a over 4 alpha x. Okay, we've just gone through. Now we can compute h at any local position x based on this assumed temperature profile. And it satisfies all the conditions that we had laid out originally. Is it perfect? Is it an exact solution? No, but it's usually really close, and it's probably useful for what you're trying to do. Okay, we can also, just to get to the last part here, we can also write this in terms of the Nusselt number. Right? That's a really straightforward thing. Nusselt, just using the definition, Nusselt is equal to the characteristic length times the heat transfer coefficient divided by conductivity. That just becomes, Nusselt is the square root of u infinity a x over alpha. It's a square root. So we can, let's compare this to the, what happened here? Okay, well, I was very efficient with my space, I guess. So we can plot this, right? We can plot this out and look at the comparison to the exact solution. So the self-similar is shown in the solid line. Integral solution that we just did is the dotted line. You can see it does pretty well, right? As we thought it would. And where is it doing really well? It's doing really well for large Prandtl numbers, where our assumption was that the boundary layer for the momentum boundary layer is much bigger than, or bigger than the thermal boundary layer. So that velocity profile is valid, right? It comes down to that velocity profile. As you get to Prandtl for 1 or less than 1, you start getting more error for the assumption that we made. Okay. Questions? We have one last thing to talk through. Okay. I do want to kind of show you how to do this for Q dot double prime S being constant. So we'll just walk through that really quickly. It's really straightforward. The idea is that here's where we left off before, where we have this governing ODE. We decided that TS was constant. And so when we solved this, we pulled TS out. If TS is in fact not constant, in the case where Q dot double prime is constant, then we have to do something a little different. So instead we just come in here and say, all right, let's write this where we're going to make the substitution that TS minus T infinity is this, right? This is what we're going to substitute in. We do know Q dot double prime, but once we make the substitution, then we end up with this ODE, which is d dx u infinity. Now it's Q dot double prime S times delta T over 2K times delta T times what was A? It was 1 over 6 square root of Prandtl minus 1 over 30 Prandtl. Okay, that's the differential. And then on the right-hand side, we again make that substitution, and it simplifies to what? Q dot double prime S divided by rho C. Okay, so again, we can just go through, solve this the same way, knowing now that Q dot double prime S is constant. I'll skip the steps, but you end up getting what? You end up getting delta T is equal to the square root of 2kx over rho C u infinity times that term A. Let's compare this to what we had before, which was what? The same thing, delta T is equal to the square root of kx over rho C u infinity A. So what's the difference? The only difference is square root of 2. So it turns out if you have a thermal boundary layer where the specified heat flux is, or the heat flux is specified, it's going to grow by a square root of 2 faster. Yes. So kind of interesting.